Morning. Yeah. So today we have with us Professor Amitava Gupta. He is very renowned scientist in the atmospheric community, particularly when we talk on ionospheric study. To give a very brief introduction, his research career started with his PhD work in 1980, which he awarded in the University of Delhi, which you can see the many of our students also from same university, means MSc from that same university. Then subsequently he joined, or maybe during his PhD awarding period, he joined as a scientist in NPL, and career started with the time standard section of NPL. And as you know, that NPL is very famous for the standard of time and other all the metrology and all those. So his career started from there. And then he ultimately retired from NPL as a director in 2015. And his major achievement, in basically I point out on in two aspects: the contribution on the accurate time synchronization using the Indian satellite INSAT. And that work has led to the providing the broadcast service from the satellite for the first time. He was also the youngest member on the first Antarctic mission expedition, that is in year 81 and 82. You can imagine, like he was just completed PhD and then joined. And first, that was the first Antarctic mission. Another great thing, he was also leading a team to set up the myriads station in Antarctic. That is around after 7 or 8 years. That is in the 1988 and 89. That of course, I think the myriads is now not working. The another station, it is working. It is working. So India has two stations now in Antarctic, and third one is also now being planned. He is the fellow of the one of the science academy in also the electronics and telecom society. At present, he is holding the honorary visiting professorship at the North Cap University in New Delhi, and he is general secretary of Indian Radio Science Society. So let us hear from him on his excellent work on the atomic clock. Professor Sen Gupta.
Thank you very much, Anishji, for that kind introduction. I am going to talk about a brief introduction to atomic clocks. I don't know, many of you have probably heard about atomic clocks. They're not like atom bombs or anything. Use atoms to make clocks. But before I start, let me just say that this is not my first visit to Aries. I came here when it was not Aries, it was UP State Observatory, Nainital. And I had just joined, as he had mentioned, the time standards of NPL, and we were broadcasting time standards on shortwave frequencies, simple time ticks, early 1980s, late 70s, and so on. And then we had heard one gentleman called S.D. Sinwal, who was from Aries. I didn't know him, and he had made some studies on our time signals and proved that we were transmitting wrong signals. We were very upset with him, but then this was in a right spirit. So we later corrected ourselves. So I really wanted to meet him. I didn't realize he was the director of the institute. So then I visited UPSO in 1985. Unfortunately, by then he had already retired, so I didn't get to meet him. But this was my first interaction with Aries. In those days, the measurements were very simple, very primitive. These kinds of receivers we used, and we used these kinds of oscilloscopes with time signals, tick, tick, tick. And we used to get synchronization at those times with ultra precision, like 1 millisecond, 1,000th of a second, which was considered a big deal. But fast forward to today, today, there are two things that we don't worry about at all. Firstly, where on earth am I? If you want to know where you are, you just push out your mobile phone, and there are GPS satellites, and they tell you your exact position. That's one thing that I'd never have to worry about, no matter where on earth I am. And the second thing that I don't worry about is what time it is, because the GPS also gives you the exact time down to microseconds or even nanoseconds, etc. And indeed, today, if I have to go anywhere, unknown place, unknown city, all I have to do is have this kind of a GPS receiver, and it just guides precisely to within a few meters or so. And also the aircrafts, when they come in, they don't have to, the pilots here don't, when they are landing the aircraft, he's just sitting there comfortably, because there are these satellites and precise positioning that takes the thing on a perfect gliding route to within a meter or so. So such is the precision of these kinds of things. And all that, all that is possible thanks to a constellation of satellites which circle around the Earth at about 20,000 kilometers or so, the Global Positioning Satellite System. And each one of these satellites carries clocks, and they transmit time signals. Very simply said, these satellites transmit time signals, and each one of these satellite time signals are precisely synchronized with each other to about a billionth of a second, absolutely synchronized with each other. And you, as a user somewhere on the surface of the Earth, receive these signals and find out the time of arrival, and hence do some computation and find out where you are, right? Now, in order for this to work, the time accuracy is very important. Why is it very important? Because what we are measuring is the time of arrival of the signal, and finding out the difference between the time of arrival from several different satellites, and using that information to compute our unknown position. Now, these signals are electromagnetic signals, and they travel with the speed of light. It takes only a one microsecond. It travels as much as about 300 meters or so. So if you have a synchronization error between the satellite clocks of roughly about a microsecond, then it turns out that the user position becomes uncertain to within a kilometer or so. So if you want position accuracy to better than a few meters, you must have synchronization between satellite clocks at a few nanoseconds or few billionths of a second. And that, unfortunately, is possible only with atomic clocks. So that's the kind of a little bhumika that I make for my talk. I mean, we are trying to describe atomic clocks, and what do we use it for? So this is what we use it for, right? So in my talk, I'm just going to give you, please pardon me, some of you are probably already aware of this. My talk is going to be very simple. No mathematics, no equations, no big results or anything. Just the basic principles of how an atomic clock works. Almost like high school physics, right? But just a brief description of how an atomic clock works. Okay, so what is inside a clock and why we need atomic clocks? This we have already described, why we need atomic clocks. And what is the principle of working of an atomic clocks, and what are the different kinds of atomic clocks? And how do we improve, how do we make better and better clocks? And what are optical atomic clocks? And some look into the future. And finally, we ask ourselves the question as normal human beings, we are normally happy with time accuracies of a few minutes. Our talk was supposed to start at 11 o'clock. It started at 11:05. Who cares? Why do I need 1 nanosecond accuracy? But indeed, there are situations where you care, right? We are going to talk about a few such things, right? So that's the outline of my talk. Now, inside a clock, the ingredient of a basic clock are basically this. Inside, there is a source of periodic motion, right? A periodic event that defines a time interval, a time period. Then there is a counter which counts how many such events have elapsed. And then finally, there is a display which tells you so many events, so, so many hours, so many minutes, so many seconds. So you quickly realize that the counter and the display unit are fairly mundane things. They don't make mistakes. So the goodness of a clock is basically decided by the frequency source. If your frequency source is very accurate, namely the time interval that it specifies is very accurate, and it's stable, it does not change with time, so is your clock, right? So finally, when we talk about really good clocks, we no longer talk about counters, display units. These are fairly mundane, either mechanical with gears, etc., or electronic counters, etc. We talk only about the frequency source. So atomic clocks are interchangeably used with atomic frequency sources and atomic frequency source, right? Okay, so inside a clock, in a normal mechanical clock, there is a pendulum which goes back and forth. Each time it goes back and forth, it says 1 second, and then there are gears. That's the counter, how counts, and then finally the display. So the best, the most ancient, most acceptable by the human beings, the source of periodic event is the rotating Earth. The Earth has been rotating like this forever, and this was the first clock that the human beings used in the beginning, right? Once in 24 hours. And at that time, this was considered, till very recently, till about 100 years ago, it was thought that this was made by God and couldn't make a mistake. So this was the perfect clock that existed. So everything was referred to this one rotation of the Earth, right? But now all that perception has changed. Earth makes mistake. It's speeding up, it's slowing down. It changes with season and so on. So then came the mechanical clock. The mechanical clock, as I said, has a pendulum which goes back and forth. And each time it goes back and forth, there's an escapement mechanism. It counts how many such oscillations have gone. And then there are displays, etc. The problem, and then if you don't want a mechanical clock, which is a pendulum clock, you can also have a balance wheel, a spring clock, which makes it more compact, etc. But there is a problem with the mechanical clock, namely the length of the pendulum or the size of the spring has to be adjusted precisely to get a certain time period. So it's very subjective. The person who's making the clock, he decides how good the clock is, how accurate the clock is, right? It's a function of the temperature too. The time period is a function of Earth's gravity. You take this mechanical clock from one place to another place, it changes its time period. So it's not universally accurate. And then there are other effects like friction, which is variable, and there are large sources of error. So it was realized about 100 years ago that the mechanical clocks, although you can make them really nice and very accurate and so on and so forth, but they're not really nice. So at the turn of the 19th century, 20th century, a major milestone, namely a quartz oscillator, I'm still getting used to this. A major milestone was the discovery of quartz, which is a crystalline form of silicon dioxide, exhibits a phenomenon, all of you know this, high school physics, called piezoelectricity. It exhibits piezoelectric effect, and namely that any quartz crystal is an elastic material, has a natural frequency of resonance and oscillation frequency. It goes ping, 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 ping at a certain frequency. And when it does that, it generates an alternate voltage across it. That's the piezoelectricity. Now, you can use that information, you can use that alternating voltage inside an oscillator to make an oscillator which oscillates very perfectly at that resonance frequency. Okay. And you can then use a counter and a divider to get a 1 second time period and make a clock out of this. So the first time this was done was not too long ago. This was done in 1927 in the US. And then it turned out that these piezoelectric oscillator-based clocks, the quartz clocks, were extremely good. In fact, if you can keep the temperature of this very constant, then this was the clock that was used to find out that indeed the Earth's rate of rotation is not constant, it changes with time and so on. So for several decades, so this became the fancy thing, the best clock in the world. So absolutely, I'm going to describe that. I'm going to describe. So the first clock, just for information, the first clock, which was built in 1932, occupied a room full of instruments, you know. And today, you wear the quartz clock on your. That's the power of technology, right? In less than 100 years, a room full of instruments gets reduced to your wristwatch, right? So, however, the quartz is also not the perfect form of clock because it has to be ground, like you said. It has to be ground to a certain thickness in order to get a certain resonance frequency. The resonance frequency is a function of the thickness of the quartz crystal. And it changes with temperature. It also has a slow variation, aging, because the quartz crystal is not ultra pure. It has impurities. So when it oscillates, the impurities redistribute themselves, and hence it slowly changes the resonance frequency. So even this quartz crystal oscillator or quartz crystal clock, it's much better than mechanical clocks, much better than the Earth's clock, but it's still not the best clock in the world. Now, several years before, you know, all these developments were taking place, 1920s, 1930s, this gentleman, all of you are very familiar with him, James Clerk Maxwell, had made a fantastic prophecy. He had said that if we wish to obtain standards, ultimate standards of length, time, and mass, which shall be absolutely permanent, then we must seek them out not in dimensions or motions or mass of our planet, but in the wavelength period of motion and the mass of these imperishable, unalterable, and perfectly similar atoms or molecules. Namely, if you have to devise a standard of time, you must look for some period of motion, some frequency inside the atoms. What a fantastic prophecy in 1870, when atoms were not even known so precisely, right? So, but however, this is the basis of our today's atomic clock. So we use atoms as tiny oscillators. How? Very simple high school physics. It's not a very complicated thing. Inside an atom, you know, we all know that atom has a nucleus, and there are electrons that go round in definite orbits. And only when an electron goes from one orbit to another orbit, it jumps discretely. And when it does that, from one energy level to another energy level, it either absorbs or emits a photon, right? And that photon has a unique frequency. That is a perfect Pakka frequency, which is God-given, right? Which, if you take an atom of gold or atom of cesium, certain energies, whether you pick it up from Nainital or Delhi or Timbuktu or anywhere in the universe, that frequency is that frequency, right? So if you can somehow extract that frequency and make a clock out of this, that would be the perfect clock in the world. That's the basis, my dear friends, of atomic clocks. And rest is a matter of details. I'll tell you very simple description of how we extract that frequency out of the atoms and make clocks out of it, right? That's the story. I will describe all that. I will describe all that in very simple terms, right? No, don't worry. He asked about Heisenberg's uncertainty principle. I said, don't worry, I'll describe that. So only, I mean, if I get carried away in such a description and exceed my time, I mean, if you think it's boring, just let me know and I'll stop. But if you don't let me know, I'll continue, right? That's the deal. Okay. So, and when did all this story begin? Using atoms as clocks? This is not very long ago. It happened in 1945, which is less than 100 years ago, only about 50, 60 or 70 years ago, right? And then this gentleman called Isidore Rabi, he was the Nobel laureate, 1944. He was giving a talk, and where he said, for the first time, he said, the atoms, the radio frequencies at the heart of atoms could be used to build clocks, etc. So then this was perfected a little bit by his student, Professor Norman Ramsay. I'm going to describe all this, right? So this is the beginning of the story, 1945. So you know, it's not too long ago. So what do we do? How we define an atomic clock or an atomic frequency standard? It's a device that makes use of a stable atomic transition frequency as its reference. A quartz oscillator, normally that transition frequency is not a very standard frequency like 10 megahertz or 100 megahertz. It's some weird number. It's some very funny number. So, and also that photon or the signal that comes out is very, very weak. So you cannot use it directly. So what you do is you use a quartz crystal oscillator, which has a very strong signal and has a very noble number, like you can have a 5 megahertz oscillator or whatever. And you usually phase lock it to the atomic transition to give a usable output. I'll explain to you in very simple terms how all that happens. So there are different steps to making an atomic clock. It doesn't move. I messed up something. There. So there are some important. Let me just test it. Yeah, right. Okay, sorry. So there are some important considerations now. The first thing is we said we'll use a transition of an atom. So now which atom? So you have to first select a suitable atom. Then you next select a suitable transition. Then you have to prepare the atoms because just a little background. See, I said the electrons in an atom go round in orbits, discrete orbits. But if you have one atom sitting there with its electrons going round, another atom comes nearby, it affects the energy levels of the first atom. If you have too many neighbors, then this energy level is no longer discrete, it becomes a band, like in solid state. So if you want discrete energy levels, which are very definite, right, you must have one atom and no neighbors. How do you get that? You get that by having atoms not in solid state, not in liquid state, as very tenuous vapors, extremely low density atomic vapors, so that you have one atom here, one atom far away. But when you have that, excuse me. But when you have that, then unfortunately, this guy, which is sitting here at room temperature, is not at rest. It's moving very rapidly. So if you have it in front of you, it takes no time, less than a few milliseconds, moving at 1 kilometer per hour, 1 kilometer per second. It'll just, so you have to prepare the atom and confine it to within your field of view. I'll describe all that. And then you have to interrogate the atom, ask it to emit a photon, right? So that's the deal. So let us see how all that happens. First of all, which atoms do we choose? Now remember, the story begins around 1945 or so. And just after 1945, end of the World War, the lasers have not been invented yet. Lasers came much later in 1960. So we cannot interrogate, we cannot deal with optical wavelength, right? Thanks to the Second World War, microwaves were highly developed. Microwave electronics was highly developed. So a suitable transition frequency would be in the microwave, right? Okay. So then it turned out that this first group of elements the group 1 elements, the alkali atoms, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, were really good candidates. Why? Because they have one unpaired electron in the outermost orbit, which have very nice energy level structure. And another very important thing is you have to detect the atoms. I'll describe that later. And in detecting, the way they describe, no optical detection, the way they detect the atoms is by ionizing it and measuring an ion and electron current. So ionization potential of these guys is the lowest, right? Alkali atoms. So that's how alkali atoms were chosen. Selecting suitable atoms, we have done that. Okay, and then it turns out that I'm skipping details. These candidates, cesium, rubidium, and hydrogen, were the ones which are ultimately used. Everything else was tested, but ultimately we used cesium, rubidium, and hydrogen to finally make atomic clocks. I'll describe how, right? So suitable atoms chosen. The next, selecting suitable transition. How do we select suitable transitions, which will be in microwaves? Okay, so this is the energy level diagram of cesium, a stable isotope. This is not radioactive, has a very large lifetime, which is a requirement for making an atomic clock. You don't want a radioactive material, which itself is not stable. So this is a stable isotope, and it has a ground state, and it has excited state. So the first excited state, and so on and so forth. Now, these frequencies are all optical frequencies. So none of these transitions is a suitable transition as far as we are concerned for an atomic clock. So now, usually in an atomic frequency standard, they are based on magnetic hyperfine transitions in ground state. Perhaps all of you are, because you are astronomers, you are perhaps familiar with ground state hyperfine transition frequencies. But just for completeness of my story, this is how it works. The nucleus is a charged particle, has a spin, so it acts like a dipole magnet. The electron is a charged particle, has a spin, another magnet. Now, these two magnets can be either aligned with each other or antiparallel to each other. Now, depending on whether they're parallel or antiparallel, there's a slight difference in energy of the electron, and that difference is the magnetic hyperfine transition. So that's the magnetic hyperfine transition separation of cesium. And it turns out that in cesium, it's a nice microwave frequency, 9.192 gigahertz. So this is what we use for our clock, right? So atom chosen, transition chosen. Now let us see how we make the clock. But before that, a little bit of detail. So we have to prepare the atoms, right? Now, in an atomic system at room temperature, everything is at room temperature. At room temperature, the atoms are distributed according to Boltzmann's law. Their population is distributed depending on their energy levels. The higher the energy, lower is the population. So because these energies are very high compared to the ground state, their population is extremely small. Most of the atoms are lying in the ground state at room temperature. All of you know that, right? But however, I know that the ground state actually consists of two states, the F equal to 4 and F equal to 3, two hyperfine states. And because these two states are very close to each other, the population of these two states is identical. They're 50% distributed among the two states, right? Okay. So a little bit about the atom-photon interaction, very simple high school physics, pardon me for this, but this is how it happens. Suppose the electron is in one of the two hyperfine states, that F equal to 3, and then I shine a photon on this system, and if this photon becomes equal to 9.192, blah, 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 then there's a resonance, this photon is absorbed, and the electron goes to F equal to 4, and the photon is gone. That's absorption. And vice versa, if the electron were sitting here, and I shine a photon at resonance, then this comes down to F equal to 3, and an induced photon comes out. These two photons are synchronous with each other. So absorption and induced emission. Now suppose I have a group of clocks, a group of atoms, extremely tenuous vapor state, not very close to each other, but a large group of atoms. Now in this system, half of the atoms are blue atoms, half of the atoms are red atoms, because they are 50% distributed among the two states. Now in this state, if I shine a photon into this system, what is going to happen is the blue atoms will absorb and become red atoms, and the red atoms will induce emission, and they will go to become blue and emit a photon. So ultimately, the same number of photons comes out, although there is a resonance. So I don't get to see anything at all. So in order to see resonance, I must do something. I must prepare the whole system, and that is called state selection. So I must somehow eliminate one of these two kinds of atoms from the system. So when I shine the photons, if there is resonance, they will go to the other state, and something will happen to the number of photons, and I'll get to know. So that state selection happens like this. Now, we can consider the cesium atoms as tiny magnets, dipole magnets, right? These dipole magnets, depending on whether the atoms are blue atoms or red atoms, F equal to 4 or F equal to 3, are either pointing one way or pointing the other way, right? Now, suppose if we pass a group of cesium atoms in an ensemble, which consists of identical, blue and red atoms, if I pass it through a strong magnetic field gradient like this, there's an atom sitting here. If it is pointing one way and I pass it through this, what happens is it deflects one way because there's a field gradient. But if there's an atom which is in the other state, it'll deflect the other way, right? So this gives me a very convenient way. I take a group of atoms, somehow force them to go through a magnetic field gradient, and there is automatic sieving. One kind of atom goes this way, the other kind of atoms this way. I can block one of them, select the others, and I've got my one kind of atom. That's state selection, right? Now let us understand the working principle of an atomic clock. With all that introduction, having selected atoms, having selected transition frequencies, having prepared the atoms, having done state selection, etc., let's put the clock together. So in the clock, what I do is I have an ultra-high vacuum enclosure, right? Ultimately, everything is inside ultra-high vacuum. I have a small oven, a small container, which has a small opening, a tiny amount of cesium element. Cesium at room temperature is liquid, right? You don't have to take too much amount of cesium. We take only 1 gram of cesium, sometimes half a gram of cesium. That lasts us for about several years because the consumption is very little, okay? So you heat up this oven, you fill this with, F equal to 4 and F equal to 3 at room temperature, 50% of the in either state. And then because there's a tiny hole here, it forms a beam of cesium atoms at room temperature. And this beam consists of both kinds of atoms, right? Now, in the path of the beam, if I put a state selector magnet, which has a strong field gradient, a tiny magnet with strong field gradient, then I achieve my state selection. I have one kind which goes one way, the other kind which goes the other way, right? So I can block one of them and use this beam as my beam to make the clock, right? State selected atoms. So then what I do is I put another analyzer magnet at the end of the path, and depending on what state this is in, it goes and deflects and hits this target, right? So and now what I do is I put a microwave cavity. I put a microwave cavity in the path of this state selected beam, And then we take a quartz oscillator and have a microwave synthesizer. All these are fairly mundane pieces of electronics as far as you guys are concerned. So then I try to synthesize something like 9.192, right? Initially, the frequency is not correct. The frequency, when I just start, the frequency is not correct. So what we do is we scan this frequency across resonance. We scan this frequency of the 5 megahertz oscillator, and hence the frequency of this microwave is scanned across resonance. And as soon as the frequency becomes equal to exactly 9.192, these atoms actually flip from one state to the other. They flip from one state to the other because there's resonance. So when they flip, what happens is this beam, instead of going and hitting this target, comes now and falls on the detector. This is a hot ion detector, and you detect an ionization current because atoms are falling on it. And that signal, you use that signal to hold this frequency to the resonance frequency. So you close this loop and use that to hold the 5 megahertz frequency on resonance. This is locking the quartz oscillator. This is how we lock the quartz oscillator with atomic resonance frequency. Very clear, no? Oh, because now the atoms are no longer the one kind of atoms. They have now flipped because we have shining microwaves at the right frequency, right? Right? So that's the simple principle. So this is the basic principle. So now what you have done is you have used a macroscopic oscillator, a quartz oscillator, to lock to the microscopic property of the atoms. You have locked the oscillator to the resonance. And and I can use this output, once it is locked, I can use this 5 megahertz output of the quartz to use as an atomic clock output because it's locked to resonance, right? Quartz oscillator. Yeah. Correct. Correct. Yeah. No. It has to look, quartz has a natural frequency of resonance, but when you use a quartz oscillator, a piezoelectric oscillator, in making an oscillator circuit, you can tune this by using a variable capacitor. You have means of tuning it over a certain range, right? That's electronics. All the guys that do electronics, for them, it's very simple. That quartz oscillator is tunable, right? Okay. So that's, please. Correct. Tune it to what? Oh, no. See, the basis of that microwave frequency synthesizer is the quartz thing. If the quartz oscillator is not accurate, your output will not be accurate. No? So I must make the output frequency accurate. So this is what I'm doing by locking that output frequency of the synthesizer to resonance of the atom. Then that makes it accurate, and so is the accuracy of the quartz oscillator, right? Okay. The state selector magnet? No, there is no splitting involved. The state selector magnet is only, in very simple terms, it is a mechanical deflection of tiny dipole atoms in one direction or another direction. There is no Zeeman splitting, right? In presence of a strong magnetic field, the atoms are split into states, but that's a different phenomenon, right? Okay. Can we use the detector here? Here? No. See, the atoms are falling here when they're not in resonance. Only when you strike a resonance, when you change the frequency of the microwave frequency, microwave synthesizer, so that it equals the atomic resonance frequency, do the atoms come and fall on the detector. Otherwise, they were going the other way. No? So why do you want to put a detector there? The atoms will be falling there anyway, even when the frequency is not right. Right? Okay. So I'll skip a few of these. I'll skip a few slides, and this a little bit more details about atomic physics, but I think I'll skip this. Now, but I mean, if you like, I'll do that, but I think I'll skip that. But now I come to the point that was raised, Heisenberg's uncertainty principle. Now, in my description of that atomic clock earlier, I very conveniently used the term that atoms are going merrily and they don't feel the microwave frequency on them at all, as long as the frequency is wrong. Now, as soon as I get the right frequency, the atoms flip. Now, in quantum mechanics, there is no such thing as soon as. There is no delta function. The atoms actually start making transitions even before the resonance has reached. There's a certain amount of uncertainty around the resonance, and that gives the resonance a certain width, right? So, and that resonance width is this central resonance width. Now, well, all this is a part of my earlier description, so which I skipped. So I think I'll skip all this too. Oops, sorry. I'll skip. So I'll come back to this description a little later. But before that, let me just show you what the world's first atomic clock looked like. The world's first atomic clock, which was made in 1955, the first cesium atomic clock. The earlier ammonia atomic clock was made some time ago, 1949 or so. But the first cesium atomic clock was made in NPL in United Kingdom in 1955. And this is how ugly and half a room full size. And today, if you have lots of money, I mean, something like 1 crore or 60 lakhs or something like that, you can buy this unimpressive looking instrument. This is the commercial cesium atomic clock, which is extremely accurate. With the accuracy of this, if you allow it to run continuously, it will lose or gain 1 second in about 30,000 years. That's how accurate it is. It's about 1 part in 10 to the 12, but it's still not accurate enough. We want it much better. Today, we can make atomic clocks which are much, much better than this. But this is good enough for most applications. And such atomic clocks are sold in the market today. Very nice and compact. Now, inside this atomic clock, I just show you the inside of the clock. There is this ultra-high vacuum chamber, this thing, and a lot of electronics. And inside this is called the cesium beam tube. You can see the microwave cavity here. There is the state selector magnet sitting on one side, analyzer magnet sitting on the other side. This is the detector. This is the oven. And the whole thing is encapsulated and evacuated. So that's inside an atomic clock. Now, this is the brief story about cesium atomic clock, right? Now, I also said you can make atomic clocks out of other alkali elements, namely, uh, you can make atomic clocks out of cesium, out of rubidium, out of hydrogen masers. Oh, what is the blocking element made of? Please use. Right. Yeah.
Hello. I was just asking that in the analyzer magnet, you block a certain set of atoms that are not different.
That's the graphite target. It just
Graphite,
absorbs.
okay. Absorbs, right?
Yeah, graphite. Graphite is a good getter material. It just absorbs, right? Okay. So there are atomic clocks not made of cesium, although cesium is the most common one. You can make atomic clocks out of rubidium and hydrogen also. Unfortunately, because of time constraints, I'm not going to be able to tell you stories of how hydrogen atomic clock is made or how rubidium atomic clocks. I'll just show you pictures of those, right? So this is the cesium clock that I told you about. If you have a lot of money, you can buy these. And if you have even more money, you can buy a hydrogen maser. This is also an extremely accurate clock. They're used in radio astronomy sites. They're very precise. They're not very accurate. They're very precise. And then you can also, if you don't have that much money, but your application requires compact atomic clocks, tiny devices like this size, and don't consume a lot of power, you can buy rubidium atomic clocks. They're based on cells. They're not beams. They're cells, rubidium. So maybe sometime if I come back later, I can tell you stories about how rubidium clocks are made, how atomic hydrogen masers are made. A very interesting story. So now, the next thing we go to in the rest of the time that is available to me is, okay, we have made a clock out of cesium. The basic principles I've told you, I've skipped a lot of details. Sorry, I've skipped a lot of details, but now I'm asking myself the question, can I improve my atomic clock? Can I make it more accurate? I showed you the accuracy of 1 second in 30,000 years or so, which you thought was very accurate. But I'll tell you, we can make, orders of magnitude better than that. And how do we do that? So in this, see, the atoms come here, interact with the microwaves and go away, right? And typically atoms are traveling at thermal room temperatures. Thermal velocities are about few hundred meters per second. And this beam, this microwave cavity is about 30 centimeters long, approximately 20 to 30 centimeters long. So it takes a few milliseconds to go through. So the Heisenberg's uncertainty principle says the delta E, the width of the resonance, the uncertainty in the energy of the resonance, delta E times this delta T, which is the time of interrogation, the product of these two must be equal to H cross. That's the Heisenberg's uncertainty principle. So if my delta T is about a few milliseconds, then it turns out that this resonance width is a couple of hundred hertz. 100 hertz in 9 gigahertz is a Q of approximately 10 to the 9 or so, right? About 10 to the 9, which is a fantastic high Q. That's how you get such accurate clock. But supposing I want to make a better clock, I must make this resonance narrower. The normal resonance is about 100 hertz or so, and I want to sit on top of this resonance. In order to get a better clock, I must make this resonance narrower so the peak is sharper, so that gives me a better clock, right? Beating the uncertainty principle. So that means in order to improve the clock accuracy, I must make the delta t longer, the time of interrogation longer. So how can I improve the time of interrogation? I can do it in this way. I can make the microwave cavity longer in size, right? The atoms will spend longer time go through it. But indeed, in the initial years, in the 1980s and early 1990s, people around the globe, in developed labs, they tried to make clocks with not 20-centimeter microwave cavities, but half a meter, 1 meter. At NIST in US, they made even 6 meters long, the size of this. But then you realize that you cannot make it infinitely long. It doesn't make sense, right? Because the atoms, they are also attracted by gravity. They will not travel in a straight line, they'll fall down, right? And also pulling a vacuum over such a long enclosure, it doesn't make sense. So this doesn't take you very much. Of course, it can get you better clocks, but this is not the way to get to much better clock. So what is the other way? The other way to make the interrogation time longer is to make the atoms travel slowly, right? You either make this length longer or make the atoms travel slowly, right? Then they will travel for longer duration. Now, when you make the atoms travel slowly, you cannot make them travel horizontally because they are attracted by gravity, they'll fall down. So in such a case, the trick is to make the atoms travel vertically upward. You make the travel, so when you have atoms in ultra-high vacuum, whether it's an atom or a macroscopic object like this, everybody obeys Newton's laws. So if I take a group of atoms like this in ultra-high vacuum and I toss it up, it just with about 4 meters per second, I give it a push, they'll go about a meter high and come back by gravity. So this is the basis of, how do I slow the atoms down? The normal room temperatures, the atoms are traveling at insane speeds, a few hundred meters per second, half a kilometer per second. So you can actually, it turns out, this was the Nobel Prize in 1997. Many of you have probably heard about this, laser cooling. Normally, it's counterintuitive. Normally, you think you shine lasers on objects to heat them up, to cut through steel, to push objects and do all kinds of stuff. But actually, you can use lasers with certain frequencies to not speed up, but slow down atoms. So that's a long story, which I'm not intending to go to. But it is such a fascinating phenomenon that these three gentlemen got the Nobel Prize in Physics for invention of laser cooling, right? So, and that laser cooling, I'm not going to go into the details of it. So you can use laser cooling to cool down a bunch of atoms. So they are not traveling very fast. They're extremely cold. They're at temperatures of a few microkelvin. At 1 microkelvin, an atom of cesium travels only at the speed of 1 centimeter per second. So if you have a cloud of atoms like this and let it be for 1 second, it doesn't really disintegrate. It just becomes a little bigger. That's all. So now if you can laser cool atoms and form a cloud of extremely cold atoms, then you can use this cloud and give it a push from below, like I said before. And then it doesn't matter whether these are atoms or an object like this. Everything obeys Newton's laws. So this whole cloud goes up like this and comes back. Now, if you put a microwave cavity in the path, it goes through the microwave cavity and comes back. And this entire thing is the interrogation time. Now, see, I said the delta T, when I was using a 20-centimeter thing, cavity and thermal atoms, was a few milliseconds. And this time is approximately 1 second. And the cavity is here to go through the cavity and back. It's about half a second, right? Approximately. So 500 millisecond compared to 5 milliseconds is 2 orders of magnitude larger delta T. So that's how we can make a clock which is 100 times, 2 orders of magnitude better than the conventional clock. So this, because we are tossing the atoms up like this is called a fountain configuration. The atoms are tossed up like a fountain. So how does this work? So I have a little animation. So what you do is you have laser beams. All these blue things are laser beams. You shine beam of lasers and make an atomic cloud and toss it up. And this is the microwave cavity. It goes through the microwave cavity and comes back. Now, unlike the description that I gave earlier, that you do state selection by a gradient of magnetic field, etc., you cannot do that anymore here, because then the atoms will go this way, that way. So the state selection here, now fast forward to today, we are not in 1940s or 50s. We can do state selection using optical beams, right? We can do state selection using optics. We can also do detection using optics. We don't have to have atoms go fall on a platinum band and ions and electrons, etc. So everything is done optically. So this is the basis of a laser-cooled cesium fountain atom, which is extremely accurate, which is 2 orders of magnitude more accurate than the conventional clock that I showed you, right? So we made such a clock in NPL. If some of you happen to be in NPL, tell me if you want to visit our lab. I'm no longer there, but I can have one of my colleagues show you this clock. So this is what it looks. This gray area is all ultra-high vacuum. You shine laser beams here. This is the microwave cavity. You toss the atoms up like this, and so on. And this is what the clock looks. I mean, it's a whole lab full of instruments. Oops, sorry. So okay. So this is where the atoms are laser cooled, and this is where, and the entire thing is shielded by magnetic shielding and all those details. And the optics is all lying here. So the optics, I just said, casually that you shine laser beams, but making those laser beams is quite a challenge. You have lots of details in that. You require 2 tables full of optics, etc., and extremely stable laser beams to do laser cooling, tossing, detection, and so on and so forth. So, and finally, I thought while we are at it, I'll show you how cold atoms look like. This is, we put a CCD camera inside, and this is a cloud of about 1 million cesium atoms, which are forming and which are tossed up vertically. So every second we form a cloud, we toss it up, and then bring it back, right? So, okay. So there are not many such fountain clocks around the world. There were about a dozen clocks around the whole world, one of which was ours at NPL in Delhi. And then there are others. One is in France and one is US. There are a couple of them in Germany and so on. Now, now I ask myself, this clock is already very accurate. It can, if you run this continuously, you can't. It's just a theoretical question because the lasers go out of clock and so on. But if you could run it continuously, uninterrupted, this clock would lose or gain 1 second in about 3 million years. That's how accurate this is. Now, then you ask yourself the question, can I make even better clocks than this? I mean, a dil mange more kind of. So yes, the answer is yes, indeed, you can make clocks which are much better than this. And the way to do that is, please. Switch.
Okay. Hello. Sir, you have shown the picture of previous cesium clock. It's almost in the box, small box
Yes.
kind of thing. But
Yes.
here you are showing it's in the
It's a whole lab.
whole lab. So how can you concentrate into this small form?
Well, wait for 50, 60 years. You'll probably wear it on your wrist. That's the power of technology. I mean, today, my cesium fountain is a room full of stuff like this. But the way things are progressing in terms of technology, very soon the whole thing is going to shrink. The entire optics, which was like a whole table full of optics, will probably shrink into a small size like this. Wait for 100 years. Ask your grandson, ask your grandchild to give you a feedback on this. He'll say, yeah, indeed, I saw cesium fountain clocks being worn on wrists. Yeah, that's the power of technology, right? Not today. Today, it's not possible. Okay.
So,
So
one more thing regarding the state selector. So, is there any preference to which state are we selecting, and does it?
there is no preference.
Okay.
You have to get it to one of the two. When you get into one of the two, when you shine a microwave, it just goes to the other one. And depending on which state you have chosen, you put the analyzer magnet accordingly. So
That's the
it
only
falls
part.
on the detector only when it flips, right? Okay. So the way to make better clocks is, remember, in a cesium clock, in a fountain clock or whatever, I'm using a resonance frequency, which is a microwave frequency, about 10 raised to the power 10 hertz. Now, the accuracy is roughly goes as delta nu, the width of the transition frequency, divided by the carrier frequency, delta nu by nu. So in case of microwave frequency, nu is 10 to the 10 hertz. But if I use an optical transition, this is 4 orders of magnitude higher in the denominator. So I can get an accuracy of a clock which is orders of magnitude better than a microwave clock. So and today I have no problems. We have lasers. We can interrogate optical frequencies, etc. So we can actually use optical. There are a lot of groups in the world, even at NPL, a few colleagues of mine, they're working on making an optical atomic clock using transitions not in cesium or rubidium or alkali atoms, but ytterbium, strontium, mercury, aluminum, and so on and so forth. So I'm not going to go into the details of all those, but just end my story here with one little cartoon here. So when I make an optical atomic clock, there are 2 ways we do it. And one of the ways is that we take not a group of atoms or so, we take just one atom and we trap it. That's the ideal situation because there are no neighbors, so no disturbance to the transition frequency. So we have a single atom, but we cannot trap an atom. We have to use an electromagnetic trap to trap an ion. So this is a single trapped ion clock. So we have an electromagnetic trap, grossly exaggerated in size. These are really tiny. So, and you put it in ultra high vacuum and you give a DC and an AC potential in this trap. So this forms the electromagnetic trap area. So you put it in ultra high vacuum and let us say accidentally an ion of ytterbium gets into this area, it just gets trapped. So when it gets trapped, it just oscillates about its mean position inside the trap. But it's still not a good enough candidate for making my clock because I want it at rest, right? So then what we do is we have a laser cooling transition, identify laser cooling transition, and shine a laser beam on this oscillating ion. So when I shine a laser beam on this, it just cools the ion down, laser cooling, right? And finally, in a few milliseconds time, very, very quickly, this ion is not only trapped, it's just sitting quietly in one place. It's laser cooled, single trapped ion. And then I have to interrogate this. Interrogate this means I have to find out, get some signals. Signals from one single ions are extremely difficult. It's a very small signal, something like attowatts of power. But such things are indeed possible. You have a photodiode detector and pick up some of the fluorescence from this. And then we interrogate the atom using the clock transition. And this clock transition now is an optical transition, not a microwave transition. So that's how you can make an optical atomic clock, which is a few orders of magnitude better than our cesium fountain clock. But the story is extremely complicated. And by the way, such a clock, if you allow it to run continuously, it would lose or gain 1 second in something like 100 million years. I mean, that's really insanely accurate, right? So, but in real life, such optical clocks are extremely complicated devices. They require huge labs full of optics and lots of stuff. So, and so on. Now, visualize these mind-boggling. When I say 1 part in 10 to the 15, 1 part in 10 to the 17, and so on and so forth, it probably doesn't register so much how insanely accurate this is. But let me just give you some kind of analogy, some example that makes you visualize these kinds of accuracy. So when I say 1 part in 10 to the 15, it's equivalent to measuring the distance between the sun and the earth to an accuracy of 0.1 millimeter. That's how accurate it's 1 part in 10 to the 15, right? And also, all of you are astronomers, so you'll understand this point better. See, when I have a frequency source, namely an atomic clock, sitting next to Earth, Earth is a strong gravitational source. Because of Einstein's general theory of relativity, there's a frequency shift, right? There's a redshift, right? Now, these clocks, I can measure the frequencies of these clocks so accurately, if the gravitational field here and 1 meter below are different. If I put my clock, instead of being here, I put it here, I can measure the change of frequency of these clocks because of gravitational redshift. So a 1 meter change of height gives a frequency redshift of 10 to the 15. I can measure that, right? In fact, one of the applications of these optical atomic clocks is to be able to measure the tectonic plate movement. They use it across a tectonic fault on 2 sides. As the 2 plates are moving relative to each other by a few centimeters, you can measure the difference in frequency between these 2 atomic clocks. And if your measurement accuracy is a few parts in 10 to the 17, you can measure easily the tectonic plate movement. That's one of the applications, right? So finally, why are we doing all this? Who cares? At least we as common human beings don't care, but there are applications where we care. Satellite navigation, I said right in the beginning of my story, satellite navigation is based on precisely synchronized atomic clocks on board satellites. High-speed digital communications, digital computations, quantum computations, geodesy, astronomy, electric power distribution, basic research, and plain curiosity, etc. Some of these applications, right? And like this is to answer you. The first quartz clock in 1932 was a big room full of instruments. And today you wear this on your wrist, right? And who knows, the same thing will happen to the atomic clock. Already atomic clocks, the rubidium atomic clock, are available in chip scale about this size. They're not that accurate, but they're available. Right? So finally, a brief summary of the history. Early mechanical clocks, a few hundred years have elapsed, and the clock accuracy goes like this. And the first cesium beam clock, 1955, since then, it has been increasing by an accuracy of an order of magnitude every 10 years, right? And we are somewhere here right now, optical trapped ion atomic clocks. They lose again 1 second in about a few billion years. And finally, I mean, it's the end of the story? No. Ultimately, a few years down the road, we'll not be building atomic clocks, we'll be building nuclear clocks, nuclear transition, which are even more precisely known and more stable than the atomic transition. Well, the future outlook, we're probably looking at atomic frequency standards. Some of you are younger enough. I'll probably not live to see this day, but atomic standards at 10 to the minus 20 accuracy. Compact, reliable, mass producible, low cost frequency standard, something, not a room full of stuff, but a small thing that you can use. And ultra sensitive, these are fallouts. Instead of clocks, you can make accelerometers, gyros, etc., and magnetometers and so on. So thank you very much for your attention. So if there are still any questions, I'm happy to answer. Please take the mic.
We talked about the accuracy and the reliability of these clocks.
Precision.
But my question is, you mentioned that probably most of these clocks will not run for 1 million years.
Correct. Correct.
So are there any efforts in making them more robust or reliable?
Yes, indeed. In fact, we never want them to run for 1 million years. If they can run for, let's say, a few years, that's good enough for our purpose, because in any lab or any place where it matters, you don't keep one clock. You keep a group of clocks. So, and the time that you take out of this is an average of all these clocks. So should one of the clocks fail, it doesn't affect your final output. So if these clocks can carry your time for a few years, that's good enough. And in fact, already now, the cesium fountains, etc., are being run continuously for a few months at a stretch. Perhaps not for a few years yet, but few months at a stretch. And there is no reason why this should not become longer. And indeed, the optical atomic clocks right now can run for a few days, but there's no reason why another 10 years later, they cannot run for a few years.
Sir, I have one question. So in the radio astronomy, radio interferometry, basically in GMRT and other VLBI techniques you have
Correct.
mentioned,
Correct.
the atomic clocks are used basically.
Yes,
For the signal detection and for the interferometry also.
absolutely.
So how do they build this atomic clock for all the antenna itself, or there is a centralized
Oh, no.
system?
There is a central one atomic clock which provides time through optical fibers to all the antennas. In fact, it doesn't provide time stamping there. The signals from the different antennas are brought to the central location, then they're time stamped where they're recorded.
So how they do it for the VLBI? Because there are different networks.
Yes. For VLBI, let's say there's a station in GMRT. So they do recording on a magnetic tape. And one of the channels of the magnetic tape is the time stamping. That is done using a hydrogen maser, which is synchronized through satellite links to UTC, right? So this recording is kept aside. Then there's a VLBI station, let's say, I don't know, in Jodrell Bank or wherever. The same thing happens. There's a separate atomic clock sitting there. It is also synchronized to UTC using satellite links. And that is the one that is used to do time stamping of that recording on mag tape. So finally, all these mag tapes are put together. And then there's a correlator which correlates these things. And then when the times match, you get fringes.
I just wanted to ask, so what kind of atomic clocks are used in GPS satellites and even Indian satellite? Like
Indeed.
and
Yes.
size?
Like,
are they built by NPL or?
No. These are commercial clocks. For GPS, the clocks which are put on board, they are not cesium clocks. What they use are rubidium clocks. These are big rubidium clocks. And rubidium, for a certain reason, of course, that becomes a long story, so I'll probably not get into that story. But to answer your question in very simple terms, all these satellite-based navigation systems, they use rubidium clocks. In some of the applications, like Galileo has used hydrogen masers, called passive hydrogen masers. But they don't use cesium clocks.
Available.
You have to have a lot of money. Yeah, but in ISRO, we are trying to develop, I'm a part of that system, we are trying to develop our own clocks. And the launch which is going to happen for the next generation, IRNSS satellites will carry one of our homemade clocks. It's being developed at SAC, Amitava.
Is there any Indian commercial enterprise which developed these? Or
Not yet,
internationally?
not yet, not yet. I wish there'd be some young person like you guys sitting here who will undertake such a development. It's not rocket science, believe me. I mean, I'm happy to help if some of you agree to do this. Thank you. Thank you.
Wide range of aspects of the talk. And again, as just a small token of memory, to remind him his journey to Aries of after around 40 years, I request the Jagdish to give Professor Sen Gupta image capture Devasthal, and tomorrow some of you like have more discussion.